Alright, now that is the concept. Let's take a look at this particle. This particle is going to vibrate up and down, and the distance advanced by the energy or the wave during that time will be a wavelength. Now take a look at it when I run it. Now you can see the particle vibrates down, back to the equilibrium, up, back to the equilibrium. One complete vibration. The distance advanced by the wave is a wavelength. Now look at the profile of the wave. We say a wave has a crest and a trough. Now here, the particle here is at the upper extreme. The particle here is at the lower extreme. And that is the difference between the crest and the trough. Okay. Let's now obtain an equation to represent a wave. Well, the equation is going to be using the definition of the wavelength. We can now use the definition of the wavelength to get an all-important equation of the wave using the wave speed. Now, if v is the speed of the wave, how do you define speed? Speed is distance divided by time. Is that right? So speed v is distance traveled divided by time. Now just look at this. If this is the distance traveled, tell me what is the time taken for this distance? The wave advanced by this distance in what time? In one period. So if this time is one period, then this distance will be one wavelength. Is that right? The wave travels a distance of one wavelength represented by lambda in a time of one period. So in this equation, if I replace the time by one period, this distance then becomes the wavelength lambda. So we can say v, the wave speed, equal to wavelength divided by the period. You see how we obtained the wave equation. And now, look at the way I wrote it. Lambda divided by t is the same as 1 over t multiplied by lambda. Now why did I write that way? Can you give me a quantity that is equal to 1 over the period? 1 over the period is the frequency. Is that right? Reciprocal of the period is the frequency. So 1 over t equal to f, the frequency. Therefore, this is the all-important wave equation. Wave speed equal to wave frequency multiplied by the wavelength. V equal to f lambda. Now, this is true for all kinds of waves. The waves that we talk about in this lesson are mechanical waves. Waves that are generated in a medium by the vibration of the particles. This equation is also true for electromagnetic waves. See, light is an electromagnetic wave. This equation is true for all kinds of waves. And that's the reason why I said it is an all-important equation. Okay, when the particle is at the highest point, it is said to be on a crest. And at the lowest point, it is on a trough. So when you talk about a full wave consists of a crest and a trough. And so wavelength can now be defined as the distance between two adjacent troughs or the distance between two adjacent crests. You see? Tell me, what is the phase of a particle on a crest? On a crest, the particle has gone all the way up. That means it has completed a quarter of a vibration. So this particle on a crest and this particle on the next crest are in the same phase of vibration. Therefore, the distance between them is the wavelength. The distance between two adjacent crests or two adjacent trough is also wavelength. So we have many different ways of defining wavelength. The distance between two adjacent troughs or the distance between two adjacent crests, they are both wavelength because that is the distance between two nearest particles that are in the same phase of vibration. Let's now talk about two different types of waves, transverse and longitudinal waves. What is the difference between these two types of waves? Now, if the particle vibration is at right angles to the direction of propagation of the wave, then such a wave is called a transverse wave. Now, what does that mean? I want you to look at the waves on this stretched spring. Now, you can see I'm going to pluck it. When I pluck it, the segment of the spring are going to vibrate up and down, and you can see the energy will be traveling along the length of the spring. Is that right? Look at this. All right. Now, the particle vibration is up and down. The energy is transmitted along the length of the road. You can see the particle vibration is at right angles to the direction of propagation of the wave. And this type of a wave is called a transverse wave. I have given a bigger diagram there. You can see when the free end of the stretched spring is given an upward jerk, the particles vibrate up and down. This is the particle vibration. The particle vibrates up and down, and the direction of the wave propagation. The wave is propagated at right angles, and this kind of wave is called a transverse wave. All right. On the other hand, if the particle vibration is the same as the direction of propagation of the wave, such a wave is called a longitudinal wave. A longitudinal wave. I have now a slinky stretched on the table, and you can see I'm going to set the particles of the slinky into, look at this, back and forth vibration. And I want you to watch how the energy gets transferred. Now watch when I give a forward push, what happens to each segment. Now, do you see a region where the particles are together and that region moves forward? See that? So when the particles are set in the back and forth vibration, what are produced? There are regions where the particles come together, and there are some regions where the particles are farther apart, and the energy travels along the length of the spring. That means the direction of particle vibration. The particles vibrate back and forth like this. The energy moves in the same direction. Now, this kind of a wave is called a longitudinal. Here I have that illustration. I have a slinky on the table, and if I push the slinky forward, the particles are set into back and forth vibration. So if the segments of a stretched slinky is given a brisk push forward, you will see regions where the segments are crowded and regions where they are farther apart will move along the length of the spring or the slinky. You can see the particle vibration is back and forth, and this is the particle vibration that will be back and forth or left and right, and the energy or the wave propagation is in the same direction. The energy of vibration is propagated along the slinky, forming, watch here, high density regions and low density regions. So in place of the crest, in a transverse wave, what you have in a longitudinal wave is a high density region. In place of the trough, you have a low density region. So for transverse wave, you have crest and trough. For a longitudinal wave, you have high density regions and low density regions. All right, I want to see if I can show you an animation of this. Now, here is a medium that contains large amounts of particles. You can see if these particles in this region are set in back and forth vibration. If you concentrate on just one particle, you see where I'm pointing? This particle simply moves back and forth. It doesn't move away from its position, so watch it. Now, in some places particles are crowded, some other places they are farther apart. You can see high density regions form and they travel along. Low density regions form and they travel along. Now, in the same way, what is a transverse wave? In a transverse wave, the particles move up and down. The energy moves at right angles. You see? So you must distinguish between a transverse wave, you have crests and trough. In a longitudinal wave, you have high density regions and low density regions. Look at another illustration that distinguishes between a transverse wave and a longitudinal wave. Now concentrate on one particle where I'm pointing. Look at the motion of that particle. This particle is now in a crest, trough, is that right? And the crest and trough advance to the right. And look at the longitudinal wave. Concentrate on that red particle that is colored red. You can see that simply moves back and forth. When it is moving to the right, it forms a region of high density. You can see high density is moving away and low density. Regions of high density and low density move towards the medium. The particles simply vibrate back and forth. I want you to understand, when a particle moves to the right, if it is in a region of high density, when it moves to the left, it is in a region of low density. So try and distinguish between a transverse wave, which generates crests and trough, and longitudinal waves that creates high density regions and low density regions. We will now obtain a